This is Physics, Lab 3. We're going to be estimating the mass of a black hole. The methods we'll use will be the momentum principle and a combination of Newton's law of gravitation. A couple assumptions here. One, that the F net on the system is due solely to the gravitational force of the black hole, and that the black hole is positioned at the origin. We have several tasks. We've got to calculate r, the radius, that's the distance from the star to the sun, or vice versa. Then we have to determine the F net, the total force on the system. We'll do this through editing and running our Python program, and then we have to calculate the mass of the black hole by taking the output of the Python routine. So find mass of the black hole. Newton's law of gravitation looks like this. However, we do not know right now the F net vector or the radius. And if we translate over here, we're looking for the mass of the black hole. So we have to find the radius and the F net vector. Once we have that, we do some rearranging. We have the mass of the black hole times the F net vector, the radius squared over the gravitational constant, and the mass of the star. And this is what we've come up with, which was the correct answer. That's some of the background physics. We have some data available. First off, the system is a star orbiting a black hole of unknown mass. The position data in this CSV file, this is what it looks like. This is the x and y values. We have a time step given to us and the mass of the star at 1.98 e to the 30th kilograms, just about the same as our sun. So we're looking first for the r vector. And this is nothing but the radius from the sun to the star. So we look into the star data file, we pull up a couple values, R1, R2. There is no R3. This would have been the Z value if it was out of the plane. We do a square root of the R1 squared, R2 squared, or the X and Y values squared, and we come up with 2.9 e to the 12th meters. Now we have to move on to find the F net. We'll be doing this in the Python routine. We'll be using the momentum principle. F equals the p dt. First, we have to calculate the change in the velocities from the positional x and y data supplied. We calculate the initial and final. Once we have that, we multiply it by the mass of the star, and we can find the initial and final momentum. Once we've got those, we move on. We take the final momentum, subtract the initial, divide it by our time step delta t, and that should give us an F net value. This is the velocity calculation. This was in the program. The only tricky part here was the delta y portion was not there, and we had to edit that. So I'll leave that for you to look at. Now calculating the momentums, the initial and the final. Here we're calculating the initial and final velocities from the index. This is once we determine the initial velocity, we multiply it by the star mass. This gives us the initial momentum. The final momentum is the star mass multiplied by the final velocity. Once we have that, we can calculate the delta p, which is nothing but the final, subtract the initial velocity. Okay, this is the F net loop calculation carrying on. Here we have delta p equals delta p divided by delta t. This is calculating here the momentum vector. Then we have F net equals delta p. In the parallel portion, this is F net parallel, delta p delta t. Once we have that, we can determine the perpendicular by taking the total force, dp dt, and subtracting off the parallel, and then we have the perpendicular. This just updates the star position. So what do the results look like? We came up with 3.04 e to the 26 for the total force vector. This is the yellow vector pointing toward the sun. The perpendicular vector, we came in with 2.7 times e to the 26th. This is the parallel translational vector. A little error there. The arrow scale, I actually used 1.5 times e to the 15th. Okay, we now have F net and R. We've calculated those out. We do the rearranging, plug that in, and we come up with 1.9 e to the 31 kilograms. That's about 10 times the solar mass of our sun. So the results, we've calculated the F net vector, the R radius, and the mass of the black hole. What's it mean? F net is a force which cannot be observed, whereas the PDT is a change in the motion. This is a cause and an effect. Force is the cause. So dp delta t is a good approximation provided that step is fairly small. Delta p delta t perpendicular relates to the turning of the star on its path, whereas delta P, delta T, parallel describes the translational motion. And this is only if that time step delta is fairly small. And what if? What if the mass of the black hole we had was replaced by something different? Could we tell the difference? No. The mass of our star is constant. The motion was the same. We wouldn't be able to see the difference. However, any mass added or subtracted from the black hole would change the force and thereby the motion.